Yeah, welcome to week 8 of this course. This is the second lecture of heat transfer. So last class was basically just an introduction. We'll be solving a problem in this class. So assume like there is a circuit, okay? Okay. So this is a voltage source. This is some electric wire, okay? So if you know electricity, the current will flow through here and electron migration will happen like this. Okay. So because of if you ever touch a wire while it's on, it's quite hot, okay? So the wire heats up as current passes through it. Like there is some equation like I square R is equal to the heat generated. It goes like that. Okay. So okay, so this is an electric wire problem connected to a live circuit. So in this case, like temperature is a function of position, right? Anywhere in the wire, like at the edge of the wire, at the center of the wire. So it will be a function of position, right? And I'll make an assumption that temperature is at steady state within the wire. So we need to, what I want you to find out here is the differential form of conservation equation, the energy conservation equation. It's a very open-ended problem. It will clear a lot of doubts. Okay, so assuming that there is a heat source, we'll model it that way, that the wire has got a heat source because of which because the current passing through it. So that's the heat being generated, which is being dissipated out to the ambient, right, from the edges. So there's the heat loss to the ambient. Okay, so last class itself, I told you that energy conservation equation and what form it will be. In this form, now, will be unsteady term dou T by dou T plus convective term. Since T is a scalar over here, alpha is equal to K by rho Cp, the thermal diffusivity, alpha del square T plus some source HV by rho Cp. Because the entire thing will be divided by rho Cp. Okay. So what are the assumptions here? That it's solid medium, steady state, and the properties of the wire, like in this case K, rho Cp, etc., they are all constant. So what will this reduce to? See, dou T by dou T will become zero because it's steady state. And there is no fluid flow inside the wire now. It's a solid medium. So the convective term will also be equal to zero. Alpha is equal to constant, so it will just remain as alpha. Alpha del square T plus HV by rho Cp equals to zero. And what is alpha? Alpha is equal to K by rho Cp. So if you substitute that, it will be what? K by rho Cp del square T plus HV by rho Cp is equal to zero. This gets cancelled. Divide this entire thing by K. So we are left with del square T plus HV by K equals to zero. Okay, so in this case, what coordinate system will be using for a wire? Look at the shape of the wire, okay? The shape of the wire is like a cylinder, no? This is the shape of the wire. So we'll use cylindrical coordinate. On drive, I shared this book by Bird with you. I told you to check Appendix B. If you go to Appendix B, like it has got the Navier-Stokes equation, the equation of energy, the equation of mass species transfer, etc. So this is like their heat transfer. So we have to look at equation of energy, not equation of motion, right? There also like we'll have to look at cylindrical coordinate because in this appendix all the equations are given in Cartesian coordinate, cylindrical coordinate as well as spherical coordinate. So let us look at the cylindrical coordinate. This is the equation of energy in terms of okay. And if you put Q is equal to k dt by dx, like this is the form of the equation. Fine. So just go to this. I shared this book on Drive. Go there and go to page 866. Or in the book it is page 850. Just have a look at this equation once. I would suggest all of you to just open your book now and check for yourself where these equations are. Okay. You noted down this equation, right? For cylindrical coordinate. Let's come back to this. Cylindrical coordinate basically is represented by the three parameters here. One is the angle theta, one is the radius r, the longitudinal direction z. So in this case, we'll make some assumptions. We'll say that the length of the wire is much greater than diameter, or L by D is much greater than 1. So you can neglect the changes in z direction. Fine. Likewise, you can take the axisymmetric like case, like there is no theta dependence. We saw that in the uh, cylindrical quid flow. So if you remember, we told that since it's axisymmetric, there is no dependence on theta direction. So here also we can neglect the spatial variation of temperature in theta direction. Okay. So now basically this is a 1D system when t varies in the r direction. Go back to the equation of energy. So this dou square t by dou theta square is not there. Dou square t by dou z square is not there. Okay. Instead of viscous dissipation, we just have the heat source term here. So we just have 1 by r dou r of r dou t by dou r. That term is only del square with the cylindrical coordinate system. So since We are neglecting the changes in theta and z direction. In r direction, what is del square? If you look at the appendix, it's 1 by r, rho to r of r. Okay. And since it's a function only of r, you can replace the rho by d, ddr of r by ddr. So now substitute this in this governing equation. Del square t plus hv by k. What do you get? You get k by r ddr of r dt by dr plus hv equals to 0. Now again hv, anyway it's a steady state, but hv can be a function of r, right? Can also depend on spatial coordinates. But to make it simple, our problem simple, this is an example problem to show you how this equation works. So in our case, we assume hv to be constant. A uniform value throughout the wire. Okay. Basically, this equation above is just a linear ODE, second order. So a couple of classes back, I showed you the difference between linear and nonlinear ODE. So just refer back to those notes. So we can solve this by hand. Fairly straightforward equation. But since it's second order, because that's del square, we need two boundary conditions. Okay, so what are the boundary conditions? Just think about it for a couple of minutes. Boundary conditions, like towards the end of last class, we discussed now the three types of boundary conditions that we have. So this is our wire. Fine. So basically, this is medium one, the solid medium, the electric wire. The fluid around it is medium two. This is the normal vector pointing outward. So the heat that is conducted to the edge of the wire will be convected out. It will be carried away by the ambient. So that's a boundary condition that we can apply. So Q1, medium 1 is equal to Q2 at the wall at capital R, at R is equal to capital R, right? And what is Q2? It is just R at capital R, T at R at capital R minus the ambient. You can take it as T infinity. Fine. And what is Qn1? Qn1 is a heat conducted at the wall minus K dt by dr at R is equal to capital R is equal to H into T R minus T. Okay. So this is our first boundary condition. Can you think of the second boundary condition? This is symmetry boundary condition. We also used it in the fluid mechanics problems. See, if you have two surfaces, like you can use two boundary conditions. For example, in Cartesian coordinate, at x is equal to 0, at x is equal to L, you apply the two boundary conditions and you solve. For cylinder, it's got only one surface, right? R is equal to capital R. So it's only one surface in the cylinder. So we apply the symmetry boundary condition, which basically says that in this cylindrical case, t is not a function of theta or z, right? Only a function of r. And in our wire, at the center of the wire, the flux is equal to 0. Okay. Had it been a sphere, okay, there we would have said that t is not a function of theta and phi, and we would have just taken fr is equal to 0. So like that. So basically, what it means that flux is equal to 0 at r is equal to 0, or qr is equal to 0 at r is equal to 0. This is the symmetry boundary condition. So what is qr? Qr is nothing but minus k dt by dr at r is equal to 0. Is equal to 0. Fine. So whatever governing equation we had, okay, k by r dou dou r of r dt by dou r, sorry, d plus hv is equal to 0, that we had now. You integrate it two times, okay. So when you integrate it once, we'll get integrate that governing equation two times. When you integrate it once, we'll get r dt by dr is equal to minus hv r square by 2k plus c1. Now you apply boundary condition 2 at r is equal to 0. What is it? The dt by dr is equal to 0. So from there you will get this is 0, this is 0, so c1 will be equal to 0. Okay. Now this equation, once you apply c1 is equal to 0, you integrate it one more time. So you will get t is equal to minus hv r square by 4k plus c2. Now you apply the first boundary condition, okay, to this temperature profile. So what's the first boundary condition? Minus k dt by dr at r is equal to r is equal to h into dr minus t infinity. Just like T capital R is using the local thermal equilibrium, right? Basically, like if you remember the local thermal equilibrium boundary condition, T at capital R solid is equal to T at capital R gas. So you apply this boundary condition and tell me what C2 value you get. I'll give you maybe 5 minutes to solve it and tell me what C2 value you get. And from there, what is the temperature profile? Yeah, I hope you got this value of C2. Okay. So what's the temperature of as a function of R profile? Should get like this. Check whether you got this. So basically, like, if I recap, I'll tell you that like this is a electric wire connected to a circuit, okay, and current flows through it. Because of current, there is heating effect in the wire, that I square R term. So because of which there's a heat source in the wire, okay. And now I'm asking you to find the temperature as a function of position in the wire. And our assumptions are that it is at a steady state within the wire. There is no time dependence. And there is a heat source because of the I square R term. There's also heat loss to the ambient because the ambient is obviously at a cooler temperature than the wire. So whatever heat is conducted to the edge of the wire, it's convected out radially because that's the temperature gradient between the outer surface of the wire and the ambient. So our energy conservation equation just reduces to alpha del square T plus Hv by rho Cp is equal to 0 because of uniform properties, steady state, absence of any liquid in the wire. Okay. So you replace the value of alpha is equal to K by rho Cp, etc. You get this kind of equation. Del square T plus Hv by K is equal to 0. Now you use the cylindrical coordinate system because wire is in the form of a cylinder. There we say that since the length of the wire is much greater than the diameter of the wire, so L by D is much greater than 1, and you can neglect the changes in the z direction. Fine. Likewise, because it's axisymmetric, there is no dependence on the theta direction, so temperature isn't a function of theta. So it reduces to a 1D system where T varies in the R direction. Theta and Z are neglected. So in the R direction, I just showed you Bird's Appendix B, the book that I shared on Google Drive. There will get all the equations, equation of motion, equation of energy, or species transport, etc. in various coordinate systems like Cartesian, cylindrical, spherical. So from there you will see that del square is equal to this term, 1 by r dou dou r of r dou by dou r. Okay, now you plug that in, so you will get k by r. Now since it's dou is temperature is a function of only of r, not of theta and z, it's just k by r ddr of r dt by dr plus hv is equal to 0. And hv can again be a function of r, but I'm assuming hv to be constant, uniform throughout the wire. So we need two boundary conditions because it's second order equation. Okay. So first boundary condition is that whatever heat is conducted to the edge of the cylinder is convected out to the ambient. So minus k dt by dr at r is equal to capital R is equal to h into t at capital R minus t infinity. And the other case is a symmetrical boundary condition that the flux at the center of the because cylinder has got only one surface. So that we have already taken as a boundary condition. So we can't, since we don't have another surface, we will look at the center of the wire. And because it's like very symmetric, the flux there should be 0, or QR is equal to 0. Therefore, k dt by dr at r is equal to 0 is equal to 0. And yeah, the governing equation will integrate once we get this form. Then we apply this boundary condition to get C1 is equal to 0. We integrate it again and we get this form. And we apply the first boundary condition to this. And we get the value of C2, which we found here. That we again plug it into the governing equation to get the temperature profile. Okay. So hope this much is clear to you. Okay. So now at R is equal to capital R, that is the outer surface. What is T of R? So if you plug in this equation, the temperature profile equation, R is equal to capital R. So this term will become 0 because 1 minus 1, 0. We'll only have this term and this term. So we will get HVR by 2H plus T infinity. R is equal to 0. What will you get? T of 0 is equal to, now this will become 0 we'll have HV r square by 4k plus HV r by 2h plus T infinity. But HV r by 2h plus T infinity already it is T at capital R. So this reduces to HV r square by 4k plus T of capital R. Now let us non-dimensionalize this using term eta is equal to small r by capital R. Likewise, a non-dimensional temperature theta is equal to T minus T infinity by T at origin minus T infinity. Origin means center of the wire. So from here we can see that theta will vary between 0 and 1. Okay. Because what are the extreme cases? T is equal to infinity at the ambient. So T infinity minus T infinity is equal to 0. Theta is equal to 0. And at the center where T is equal to T naught. So T naught minus T infinity by T naught minus T infinity, which is 1. So this is our non-dimensional temperatures range. Theta is equal to 1 at R is equal to 0. Theta is equal to 0 at R is equal to infinity. That is very far from the wire. Okay. Now this equation, temperature profile equation, you represent it in terms of theta and eta. You tell me what is theta. You represent theta in terms of eta. I'll give you another hint. There is something called Biot number. This HR by K. So you represent theta in terms of eta and Biot number. Okay. So maybe take 5-10 minutes and let me know what expression you get. I hope you got this expression. Okay. So again, this HR by K, you will come across a similar term in the future again. So I'll just make a distinction now itself. So in case of solid, Biot number is equal to HR by K of solid. And there will be another term you'll have when we come to convection, we'll see Nusselt number. That is also HR by K. But that K is K of fluid. So note the distinction. Okay. So this is our theta 2 plus pi out into 1 minus theta square divided by 2 plus pi out. And theta already we know, it's just non-dimensional temperature. Fine. So T infinity, that is the ambient temperature. If you see that, it is just specified in the problem. It doesn't depend on the type heat source in the wire. So it's independent of heat source. T naught, if you see, T naught is equal to hv r square by 4k plus T at capital R. T at capital R is hv by r by 2h plus 2 infinity. So that depends on the heat source. So T infinity is independent of the heat source. T naught depends on the heat source. But if you see this non-dimensional temperature, theta is equal to T minus T infinity by T naught minus T infinity. This expression, there is no HV, right? This biot is just HR by KS, theta is R by capital R. So the theta is independent of heat source. So T infinity is independent of heat source. T naught is depending on heat source. But when you combine T naught T infinity, you get some non-dimensional temperature known as theta. That theta is also independent of heat source. So in the dimensionless form, independent of heat source. Okay, now let us just plot, say, theta is in the x direction, theta is in the y direction. Theta, as I already told you, it can go from 1 to 0. Theta can also go from 0 to 1. When it is 1, when r is equal to capital R. So r by r is equal to just 1. And at origin, it is r is equal to 0. So theta is equal to 0. Okay. So at various Biot numbers, what is theta? This is our expression, right? I'll just write the equation in the small form over there. So theta basically here we got theta is equal to 2 plus pi out 1 minus eta square divided by 2 plus pi out. Okay. So when biot is equal to 0, theta is just 1. Biot is infinity, right? We can neglect 2, 2. So it's just biot into 1 minus eta square by biot. Or theta is equal to 1 minus eta square. Again, when eta is equal to 0, theta is equal to 1. And when theta is equal to 1, theta is equal to 0. So it will be like this. When biot tends to infinity, theta is equal to 1 minus eta square. So eta is equal to 0, that is over here. theta is equal to 1. If theta is 1, theta is equal to 0. So this is for biot is equal to 0 case. This line, this curve for 1 minus theta square, like a parabolic curve. So as you increase biot number, curve will fall like this. So this is biot is equal to 0.5. This is equal to biot is equal to 1. So this is how the curve will look like. Right. So like the two limiting cases that we saw, biot is equal to 0 or tending to 0, very close to 0. Theta is just 2 by 2, right? 2 plus 0 by 2 plus 0. So theta is equal to 1. And what is theta is equal to 1 means? Theta is what t minus t infinity by t naught minus t infinity. So t is equal to t naught. So whatever at the center of the wire, whatever temperature, that's the temperature profile throughout the wire. So this is when biot is very small. T is equal to t naught. So this is called the lump modulus case. When biot is infinity, theta is equal to 1 minus theta square. This is the other extreme. And all other cases of biot number are in between these two extremes. Okay. So for biot number is equal to 0, how does temperature vary as a function of R? So it can go from T naught to T infinity, right? But biot tends to 0. T is equal to T naught throughout inside the wire, right? The wire is radius R is equal to capital R. So till here it is T is equal to T naught throughout. And outside it's T infinity. So that's a drop off like this. Fine. So this is biot is equal to 0. This is your lump system. Second case is when biot is very large, biot tending to infinity. How will the profile look? So the center at T is equal to R is equal to 0, T naught. And it varies as 1 minus theta square, no? So at R is equal to capital R, it's just T infinity, no? Because your theta goes as T minus T infinity by T naught minus T infinity. So at theta is equal to 1 minus theta square, that means theta is equal to 1, R is equal to capital R, it's equal to 0, theta is equal to 0, T is equal to T infinity. So it will fall like this. T naught inside the wire, it will fall like this. This is R is equal to capital R. And outside it is at T infinity, ambient temperature. Okay. Okay, so that winds up this class. Next class we'll do a lot of problems, okay, related to conduction, critical radius, and I think sir will cover external surfaces for that also. So next class we'll solve a lot of problems, okay, like 6 problems that we will try to solve. Okay, thank you.